Hi, Algebra 2. In this lesson, we're going to be taking those linear functions that we started working with and doing more transformations with them. And we're going to be introducing how to do it with function notation. So that's going to be kind of the big change in this lesson. Here we go. All right, this table is going to be really important for you to refer back to for how to do these transformations using function notation. When we say function notation, we're talking about these things here when we name functions using things like f of x, or you could have any letter there. Let's first talk about a vertical shift. If you're shifting something vertically, we know that it affects the y values or the outputs of the function. And so we're just going to take our whole function and then add whatever that shift is to it. If you end up adding, it moves it up. If you end up subtracting, it moves it down. Horizontal is a little bit different. Horizontal shift will affect your x values or your input. And so you see that affecting the x values here in function notation. And it's weird that if your h is greater than 0, which means you can have x minus h, it's going to move to the right. And if h is less than 0, which means you're going to end up with x minus a negative h, it's going to move left. So it's kind of opposite of what we think, but that's going to be the way that it works. Reflections down here. Reflecting across the y-axis affects your x values or your inputs, and so we end up with f of negative x. The inputs are going to end up being the opposite. Reflections across the x-axis are going to affect the output, so the whole function ends up being its opposite or its negative. Okay, our first transformation we're going to do is a vertical translation 4 units up, but first thing is to just review slope-intercept form because it's going to make it easier to graph these. Remember that your slope, which case we call m, is the number being multiplied by x, and then your y-intercept is b. So the first thing I want to do is just graph our original function, f of x equals 2x plus 3. 3 is my y-intercept, and my slope is 2, or 2 over 1. Think rise over run, and there it is. Okay, now we're going to do the vertical translation 4 units up. From your previous table, you know that vertical translation is going to affect your y values or your output. And if we go up, we're going to be adding 4. So we're really taking our whole original function, f of x, and adding 4 to it. Now I'm going to simplify that. Instead of writing f of x, I'm going to write my original function and then add 4 to it. I don't really need those parentheses there, but it's just kind of helpful to see what's going on, and I can simplify this to 2x plus 7. And that really is your answer for this problem. But just to visualize what's happening, it's nice to be able to graph it. So I'm going to put those points on here, and you can see then that we did, in fact, move each of these points up 4 units. Okay, to start this one out, I took my original function f of x. I did create a table of values here. It's going to make it easier in this problem. And I also graphed it so we can visualize what's happening. Now we're going to find g of x, our new function. And it's going to be given us by the rule f of x minus 1. So this means that our inputs are now going to be x minus 1 instead of x. And so to find g of x, I'm just going to rewrite my function. But instead of x, I'm going to have the input x minus 1. So notice that that was the function f of x, but instead of x, I put in x minus 1. And I'm going to simplify this algebraically, use a little distributive property, and we get 2x minus 1. So that's our rule for g of x. So once you plug in those x values into g of x, get your outputs, and graph it, and I'm going to zoom in here a little bit so that we can see that what happened was we had a horizontal shift of 1 unit to the right. And that makes sense because according to our table from before, that x minus 1, or f of x minus 1, would mean a horizontal shift to the right, 1 unit. Now you need to either use the QR code down here to open up Desmos, or use the link on Edpuzzle to look at some more examples. Okay, this Desmos calculator is just kind of nice to verify what's happening with these transformations, right, left, up, and down. Our original function is g of x equals 2x. That's what you see right there. If I open up the first one, g of x minus 2, I can see that it did go to the right 2 units, so that x minus 2 is causing it to go to the right 2 units. The next one, g of x plus 3, you'll notice that it goes to the left 3 units. And then the last two, minus 4 and plus 3, being done to the entire function, that's going to affect your y values. That's going to make it go up and down. Okay, in this one we're looking at a reflection. This is our original function right here. They just give it to us as a table, so I graph those points, draw that line, and we're going to be reflecting across the x-axis. Okay, I know that when I reflect across the x-axis, it's my y values that are affected. And so g of x is going to equal negative f of x. What's going to happen is that all of those f of x values just become their opposite. And then when you graph those, you should be able to see that, yeah, this was a reflection across the x-axis. Okay, this table is going to be summarizing your horizontal stretch and compression and what it looks like with function notation. The weird thing here for a horizontal stretch is that it's going to be affecting your x values, which makes sense, as you can see on the graph here. But the factor that you multiply is 1 over that factor that you're stretching. So if you're stretching it by a factor of 2, here you're going to write 1 over 2. For vertical stretch or compression, it's affecting your y values or your output, and so you get to take just the whole function times whatever factor that is. Okay, in this one we're going to be doing a horizontal compression by a factor of 1/2. Horizontal compression is when it affects the x value or your input, and that's where you have that weird 1 over whatever your factor is. So my new function is going to be f of 1 over 1/2, that's the factor, x. And so I'm going to simplify this first. 1 divided by 1/2 is 2, so I have f of 2x. So that means my new function, I'm going to plug in 2x wherever I saw x. And so I end up with negative 2x plus 4. And if you graph these just to check, it does look like a horizontal compression. Every point is now 1/2 the distance away from the y-axis as it originally was. Now we're going to do a vertical compression of the same function, f of x, by a factor of 1/2. So my new function, g of x, is going to equal 1/2 times the output of f of x. So this one's a little bit easier in that you're just taking the whole function and multiplying it by 1/2. And so if I write my rule, I'd have 1/2 times my whole function f of x. So that's going to be negative x plus 4. And I simplify algebraically my distributive property. Right here, right there. And there's my new rule, negative 1/2 x plus 2. So now I can graph that and see if it does look like a vertical compression of 1/2. Once I graph it, it does look like a vertical compression of 1/2. Notice that this intercept stayed the same and that my y values are now 1/2 the distance away from the x-axis as they originally were. Now we're going to be combining transformations, doing 2 transformations to the same function. Our original function is going to be f of x equals 3x, and we are going to be moving that left 6 units. That's what we're going to do first. So I'm going to write down my rule in function notation. So h of x is going to equal f of x plus 6. Remember, left 6 units means you're going to be adding 6 to those inputs, which I know is weird again. So instead of x, I'm going to write x plus 6. And I'm going to simplify that using distributive property, so I end up with 3x plus 18. Now for a second transformation on this function, we're going to do a horizontal stretch by a factor of 4. So horizontal stretch means that it's again going to affect our inputs. And this is where you have that weird one where you have to put it 1 over the factor. And so I end up with h of 1/4 x. And so my final rule, g of x, I'm going to look at h of x right here, and instead of x, I'm going to plug in 1/4 x. And if I simplify, I end up with 3/4 x plus 18. Now this function is kind of hard to graph on this one right here, just because of the number size. But if you want to use Desmos to double check that, feel free.